Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
All right, let's move on to lesson 8.1.2. In this lesson, I am going to introduce you to what makes the financial world go around. It's called compound interest, and we're going to reflect a little bit on simple interest, which you may have learned in 6th grade, but for sure we touched upon it last year in 7th grade because it was a part of proportional reasoning that was such a big theme of 7th grade math. But really, in reality, you just don't get simple interest. It just doesn't happen unless you're doing something very informal between friends or a parent and a child. You're never going to have a simple interest type of a situation. Everything's going to be compound interest. So, what makes compound interest compound instead of simple? Well, compound interest is interest earned not only on the original principal, but it is also on the interest that has already been earned. Okay, so with the simple interest, we saw that you would have your original principal, and then after a certain amount of time, you just calculated the interest. And the interest was based on how much time had gone by. And it was like a one-time transaction. Or if you did it like every single month, it would always be the same amount every single month because it was always being based on the same original principal. But compound interest is a little bit different because after, say, a month, you earn some interest and now you've got a new balance. And now all of the new interest that you earn is going to be based on your new balance, not on the original principal. So it keeps growing and growing and growing. And that growth becomes exponential, as you will see as we proceed through these next 2 units. So it was kind of important for us to talk about the difference between an exponent and a base because, compound interest is exponential growth. There's going to be some exponents involved in the figuring out of these problems. So I figured we should go back to this simple term, a power. So remember, this is an example of a power where you've got 2 to the 4th power. Every power is made up of 2 principal parts. One of them is the exponent. The exponent is the part of the power that tells you how many times a number is being multiplied. So this right here would be your exponent, the number 4. And the base tells you, or your base simply is the number that's being repeatedly multiplied. So the base would be the 2. So in this situation, what we have here is a shortened version of a repeated multiplication statement where 2 to the 4th power technically means 2 times 2 times 2 times 2. 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. So 2 to the 4th power has a value of 16. So understanding how exponents work is kind of important for you to understand how compound interest works. All right, so let's read. Not 2, that's an S. So far in this course, you have studied simple interest, which only pays interest on the amount invested. That's what we call the principal. It might be used for informal loan arrangements made between parents and children or between friends. Yes, I said this. Okay. However, banks and other financial institutions calculate interest a different way. They use compound interest. Okay, so we're going to learn more about that. In yesterday's lesson, we had 2 types of problems. We had a simple interest bank balance problem, and then we had the growth of the price of the baseball card problem, where it kept increasing by the same percent every single time, but the dollar amount changed every single time. So in this lesson, you will learn about compound interest and how to create an expression to describe this nonlinear growth. Continue to ask these questions or reflect upon these questions as you work today. What patterns do you see, and how can we show the connection? All right, so Ms. Hartley won about $20,000 in the lottery. She decided to spend half of it right away, but then invest the other half into an account for her retirement. The interest rate on the account Ms. Hartley chose is 5%. She calculated that after 10 years, based on simple interest, her account balance should be $15,000. However, the bank told her that after 10 years, the account would be actually a bit more, $16,289. So let's just review how simple interest works so that we can see how Ms. Hartley determined $15,000 would be her new balance. Simple interest is a proportional type of a situation where you take the amount of money that's going to be earned over every time period and multiply times the number of time periods, and that will tell you the amount of interest that has been earned on that account. The principal is the amount that is deposited, and the interest rate needs to be written as a decimal point. So in this case, the principal was 10,000, the interest rate was 5%, which is written as 5/100ths in decimal form. And the amount of time in this case is in years, and more specifically, we're going to figure it out for 10 years. So we'll multiply 5% times 10,000 to figure out the amount of interest earned would be $500 per year. So if we multiply that times 10, we get interest earned is 5,000. Therefore, the new balance would take the 10,000 that she deposited plus the 5,000 that she earned to make 15, or to have a total of $15,000. So that's how the simple interest works. A financial advisor explained to her that the bank is paying her compound interest. That means that the bank is calculating the interest each year on the total of the principal and any interest that she had earned so far, rather than just on the original principal of $10,000. If Ms. Hartley leaves the money in this account for 30 years, her $10,000 will eventually grow to more than $40,000. So to help Ms. Hartley see the difference between simple interest and compound interest, her advisor made her these following tables. All right, so remember what we did over here, that the amount of $10,000 at 5% interest would result in $500 of interest per year. So that's how I've written this here. 5 per year, and you can see, the table is showing every 5 years it goes up a certain amount of money, right? Is that constant growth, or is that something else? Here in the compound interest, we haven't yet learned the formula. It's going to work for this. Every 5 years, you can see it's not going up by the same clean amount. Okay, so this is what we call the exponential growth. It's a non-linear graph, going to show a curve to it. This is constant growth. This is going to show a graph with a straight line. So explain how you see the interest growing in the simple interest table. Well, if every year it goes up by 500 every 5 years, you can see it's going up by $2,500. And then explain how the interest grows in the compound interest table. Well, that is not growing by a constant amount. And I didn't feel like going through and subtracting each one of these and telling you the amount that it grew every single time. Feel free to do that if you want to. Just know that it's not going up by the same amount. The amount that it's increasing by is growing every single 5 years. So after 3 or 30 years, how does the simple interest balance compare to the compound interest? Well, here's the simple interest, and here is the compound interest. You can see that's significantly higher, right? In 30 years, it grew by $18,219 more. So this is going up. This $10,000 increased. What was that, the new balance? Oh, I guess it increased by $15,000 because she started with 10. That was her money. But then it's worth $25,000 at the end. So that means that the bank would have given her, I should say, $15,000. But here, in a real situation with the bank, she started with 10,000, but after 30 years, it was worth 43. So the bank had given her $33,219. So compound interest is the way to go. And you're looking at a situation like this and thinking, well, why on earth would a bank do that? Why would they pay compound interest instead of simple interest, knowing that they just have to give away that much more money? And the answer is this. No bank is ever going to pay 5%, ever. However, when a bank gives out a loan and you have to pay them back the loan, they will charge you 5% or even higher. So if you were to find a bank that would give you more than 1% on a savings account, I'd be shocked. I think my savings account for my family right now is paying like 1/10%, or it's just terrible. It's very, very low. It's like, I won't go into details, but banks do not pay you high interest rates for savings, but they will charge high rates. So if you turn this into a loan, you can see why the bank would want to go with compound interest for the loan, because you're going to be paying them the $33,219 instead of them paying you. So that's why credit card companies, and that's why bank loans, mortgage lenders, all of them do everything with compound interest. All right, compound interest is calculated on all the money in an account at specific points in time. Each time interest is calculated, it is based on both the principal amount and any interest that has been earned before. Okay, have we said this enough? We'll probably say it a few more times. This is similar to how the price of the baseball card grew in problem number 3 in the previous lesson. In that situation, each price increase was based on what the seller had paid, not what the card had originally cost. All right, so Mariana's grandfather invested $500 for her college tuition in a savings account when she was born. The account pays 5% compound interest every year. No, it doesn't. That's a completely ridiculously high interest rate, but for the purposes of mathematics and you seeing a nice clean number over here, we're going to go with it. Okay. So this resource page is available to you on the online book. It's in the Google math class. Print it off. You know the routine. I've said it 100 times. Feel free to print it off, or you can just copy all this stuff down into your journal. Okay, so it says, how do you find the new balance each year? Complete the middle column table. All right, so the middle column is this column right over here. So what we are going to do is this. According to this pattern, what we have to do is we have to take $500 and increase it by 5%. And so you might be wondering, well, why are they multiplying times 1.05? That's not 5%. That's technically 105%. All right, let's go back to a brief lesson in 7th grade math. 1.05 is the sum of the number 1 and the number 500ths, right? 1 and 500ths. 1 is equivalent to 100%. And so that's what this is saying here. Having this as your multiplier, remember our percent increases last year? The multiplier being 1.05 implies that you're going to pay 100% of, or I'm sorry, you're going to receive, this isn't a loan, this is a savings account. You're going to receive for your new balance after 1 year, 100% of what Mariana's grandfather had invested, $500, plus the 5% increase, which in decimal form is 0.005, 500ths. So you may recall last year when we talked about how there were 2 different multipliers that would apply to this situation. You could either figure out what 5% was, which would be $25, and then add it to the original amount to get $525, or you could have just multiplied times 1.05, and that would have given you the new amount right away. So we're doing this. Rather than every single transaction finding 5% of that number and then adding it, we are just going to do it in one step as a multiplication process. So we've added 1 plus the 5% together before we created this multiple. Okay, so now what I would like for you to do is this. Oh, let me go back and just show you one more time, just to make sure that you know what we're going to do here. Okay, so here's the table. We know we're starting with $500, so just grab your calculator and take $500 and then multiply it times 1.05, and you get $525. Okay. Leave this in the calculator. Do not change anything. Just leave it in there, and we're going to go to year 2, and we're going to multiply that amount times 1.05 and hit the enter button again, and you get $551.25. Leave that in and multiply it again times 1.05. And now you're going to have to round that to 578 point, looks like 812. So we're going to the nearest penny, 2 decimal places. So that 1 has to stay as it is because this isn't a 5 or greater. It's just a 2, which is lower. So we keep it the same and call that 81. Keep doing this until you complete the table. And the table takes us all the way out to the 8th year. Okay? Once we do that, then we can figure out how much total interest had been earned up to that point by just looking at whatever you added to the 500 was 25, so that was $25 in interest. Whatever was added to the 500 here, that's $51.25, and so on and so forth, all the way down. Once we've taken care of that, then we are going to graph, and I'll graph it with you. Okay, so go ahead and pause and get all that taken care of, and all the way through year 8, and then I will do the reveal. All right. Hopefully you've got this taken care of. Pause it quickly before I start revealing if you are not done and you want to wait until you're done. If you're ready, I'm moving forward. All right. So if we continue with the process, we're now going to take $551 times 225, and you get 578.81. Multiply that times 1.05, you get $607.75. Multiply that times 1.05, and you get $638.14. Multiply that, and you get $670.05. Multiply that times 1.05, you get $703.55. And the last transaction after 8 years, there would be $738.13 in the account. So, to find the total amount of interest, just take this number, subtract away 500, and you will get $78.81 as your interest. After 4 years, you have $107.75 of interest earned. After 5 years, $138.14. After 6 years, $170.05. After 7 years, $203.55. And after 8 years of just letting the money work for you in the bank, earning interest, you've increased your dollar amount by $238.73. So if I want to graph this, I'm going to either have my time be my x. I'm sorry. The time is definitely going to be your independent variable. That is going on your x-axis. But we're either going to graph the total balance as our dependent variable on the y-axis or the total interest earned. Let's look and see. They want us to graph the total interest earned. So we're going to take this column here with this column here, make this our x and that our y. So let's go ahead. The first point is 0, 0. I'm sorry, this is going to be really annoying here. I'll do this in red. 0, 0 is right there. And then the next one was 525. Oh, no, it's $25. So after 1 year, you made $25. What is that? 2, 4, 6, 8, 10. So between 2 or 4 and 6 is right around there. After 2 years, it's 51.25. So 2 years, 51. 25 is probably somewhere in there. So far, it looks kind of straight, right? But we'll see it eventually start to curve more. Then 3 years is 78.81. 3 years. What are we moving over here? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So what was the number? 71? 78.81. So 78.81. Here is that one. So 1, 2, 3, 4. We're going to go down just a little bit. All right. The next one is at 107.75. 107.75. So 4, right? 1, 2, 3, 4. Is that it? Oh, this is killing me. Hold on. It's gonna go right. It's gonna go right around there. Okay, that's a much better technique to use. So 2, 4, 6, 8, 107.75 is gonna be somewhere around there. Okay, and then year 5, is gonna be where? $38.14. $138.14. So I'm on this line, a little bit below it. Okay, and make sure that's the right one. Yes. Yes. $203. Wait. Oh my gosh. We're gonna get off the page. Wait, did I do it already? Was that 100? Oh, I never did this one, did I? Sorry. 100. Wait. 138, 170. That's the one I need. 170.05. Go up a little further. That's it right there. 170 and a little bit over that. Put it like that. And then the next one, I don't think I can graph it because the next one's 203 and we're running out of room there. But that gives us enough. Now look at that. Does that look like it's curving? No. I know it doesn't look like it's curving, but it is. Trust me. Let me take a line. This one right here. I'm going to thin it out a little bit. I'm going to go right through those 2 points. You see it curved? It's going up a little bit. It's not a perfectly straight line. So as this goes on, once you get to like the 12th or the 15th or the 20th year, you're really going to see it start to skyrocket. You'll start to see the curve. Now, because this was such a high interest rate, the 5% interest rate, it really started going off early. Generally, these have a much lower interest rate and they start out like this and then eventually start to climb. You get that low time period where it's hardly growing at all for quite a significant amount of time. In the last 5, 10, 15 years, it really starts to skyrocket. So, yeah, that's how all this works. All right, so let's come back to here, make sure we answer these questions. How do you find the new balance each year? Well, we find the new balance by multiplying the previous balance by 1.05. We've done all that. Yes, let's move on. All right, so Mariana is curious about how much money will be in her account when she's 18 and graduates from high school. She went back to the table she had created. As she looked at the numbers in the first 2 columns, she noticed a pattern that she thought she could rewrite into a shortcut. Study the table and her work. Notice what the pattern is. What is happening in this situation? And I think you start to see that she multiplies an additional 1.05 every single year. So in the first year, she multiplied it 1 time. In the second year, she did it twice. In the third year, she did it 3 times. In the fourth year, what is she going to do? She's going to do it a 4th time, right? So in Mariana's calculation for 2 years, what does the 500 times the 1.05 represent? What would that be equal to? Well, we've got what it's equal to right there, but that is the balance for the first year, right? Because in 1 year, it has grown by 5%. So you got 100% of the deposit plus the additional 5%. That's your 1.05. So how could you rewrite Mariana's balance at the end of the year in terms of principal? Well, this would be the generalization in words. For any number of years, the principal is multiplied by 1.05 the same number of times as the number of years. So it would be like in year 5, you would say 500 times 1.05 times 1.05 times 1.05 times 1.05 times 1.05, or isn't there an easier way to write that as an exponent? Let's just do it this way. We're going to take whatever the original principal was, multiply it times 1.05 because the interest rate was 5%, and then we raise that to the power of 5 because that's the number of years that this has been compounding. So that'll be interesting to see if that always is the case for every one of these compound interest problems, to the point where we could come up with a formula that might actually work for us. So based on this pattern, describe how you would find Mariana's balance after 18 years without first finding her balance at 17 years. Okay, so this is the part where it's like, if you're going to figure it out after 1 year, remember what we did on the calculator where we just kept taking the new balance and multiplying times 1.05 and rounding to the nearest penny? Well, if you did that 18 times, you would see what the balance was every single year, including the 17th year. So it's this approach that we would take to figure out what the balance would be after 18 years, where we're going to make A the new amount. The principal is going to be this number that's on the outside of the parentheses. And then whatever the interest rate has to be added to number 1 to make it 100% plus 5% is 105%, so 1.05 in decimal form. And then the times, or the number of times it's being compounded, would be the 18, right? Because it's once per year for 18 years. So to do this, I would recommend not, let me just show you. There are some scientific calculators where you can plug this entire thing in, like the Google scientific calculator. I should show you that in a second, and I will. It allows you to put everything in and then hit the enter button, and it'll tell you the new amount. On the calculator, depending on the nature of your calculator, how much time do we have here? Oh, we're good. Okay. You might need to do it in a different order. For instance, this calculator requires me to do the exponent first according to the order of operations. And this button right there, x to the y power, is the specific button on this scientific calculator that allows me to do this transaction. I'm going to hit the button, and it's going to put this upside down. It's kind of like a teepee kind of a thing, but we call that in mathematics a caret. So 1.05 caret, and then with that in there, we've raised it to the power of, I'm going to enter in the number 18, and it will take care of all the calculating for me. And you see how if I leave this number in the calculator and then multiply times 500, I'm going to get the most accurate answer. If I had to record this, I'd have to round it at some point because I'm not going to record everything there. So I chose to round it to the hundredths place, so that would be 6 makes us change that to 1, so 2.41, right? So that's why I put the kind of approximately squiggly sign. It's not exactly 2.41. To find the exact answer, I'm going to leave this in the calculator, and now I'm going to multiply it times 500. And that's going to give me a number that I have to round off. And this one, I will round off to 31 cents, $1,203.31. So our new balance is going to be $1,203.31, meaning that after 18 years, let me go here, the amount of interest that she has earned in 18 years would have to be $703.31, because 500 was already hers, but this is how much she's got now. So you subtract those, and that's how much the bank has given her. Okay. All right, so what is the formula for compound interest? Please write this down. Your life is going to be so much easier with this formula in hand for any time you've got any sort of a compound interest or compound growth type of a problem. The formula says to take A equals P, parentheses, 1 plus R, T. What do all these mean? A is the new balance. P is the principal. R is the interest rate. And remember, the 1, that was like when we were saying 100% of the previous balance plus an additional whatever your interest rate is. We will always find the interest rate and add it to the number 1 and write it as your multiplier here. And then your time is the number of times that it has been compounded. If it's compounded, yeah, I'll just leave that there. If it's compounded once a month for 12 months, then the number is 12. If it's compounded once a month for 2 years, then this is 24. If it is once a week for 3 years, 52 weeks per year is 156 times it's going to get compounded. So the T is the number of times compounded, okay? So write all this down. In fact, why don't I just go ahead and pause it, and then I will finish writing down what each one of those. I know you heard me, but I'll write it for you so you can copy. Alrighty, there you go. Copy that down. All of this is associated with the compound interest formula. Pause it. I'm going to move on. Pause it if you need to keep copying. All right, so let's just get some generic rules down here. We already talked about the powers being part base, part exponent. So the pattern you described in words in part or problem Ch8, 15 can be rewritten using symbols using an exponent. Sorry, I'm having trouble reading right now. For example, 4 times 4 times 4 times 4 times 4 can be rewritten using the base, which is the number being repeatedly multiplied before, and the exponent, the number of times it's being repeatedly multiplied. Okay, so write the numbers you multiplied in part D of problem number 15 as an expression using an exponent. We've already copied this down. That was this, $500 times 1.05 to the 18th power. Now, let's try a new one. Let's take this comic book is purchased for $6. It is resold 7 times, and each time it is resold, the seller charges 15% more than he or she paid for it, okay? So how would this look? The principal is going to be $6, right? That's how much the book originally cost. The interest rate is going to be 15%, which as a fraction or decimal would both read 1500ths. The number of times it's being sold, that's the number of times we're going to compound this with this 15% interest, would be 7 times. So let's go ahead and set this up using our formula, where we're going to plug in the principal was $6. The interest rate is added to the number 1 to make it 1.15, and then the number of times being compounded is 7. Go ahead and pause and get your calculator, and if you've got a type of calculator that allows you to put the entire expression in, go ahead and do that. But it might be easier to just take 1.15, raise it to the power of 7, and then multiply times 6. If you don't have a calculator that can do this, I would recommend getting one from Walmart or Target or any store that sells scientific calculators. They're only about $10. They're not expensive, and they will literally last you all the way through high school and college and after college, if you take care of it, of course. That being said, there are plenty of calculators available online. You can just go Google scientific calculator and find the button. Oh, I was going to do that. Okay, hold on for a second. Let me. Well, you can watch me search. Let me pull this guy up. Stop it. Let me go to scientific calculator. It knows what I'm looking for, so I click on that. And here's the scientific calculator. So there's the button you would use. So remember, it was $6. Parentheses, 100% of that plus the additional 15% is 1.15, end parentheses. Now raise that to the power of 7 because that's the number of times it is going to be sold. Okay, so are you ready? I'd highly recommend you do this as well so you get to practice using the scientific calculator, but that's all you ever have to do. Now when we hit the enter button, we're going to have our answer. Equals $15.96. So let's come back here and see. Oh, I didn't even do it. Didn't even declare my answer. Why would I not do that? Okay, I guess maybe I was planning on doing it with you. So the new amount is equal to, what did we say? $15.96. cents. That is what the seventh person will pay for this fantastic comic book. All right, I think that ends it for today. That was, oh no, got one more? Oh no, we do have to do this. All right, so here we go. Copy this down. I'm so sorry, this is taking a long time. It's a long lesson, but it's an important lesson, okay? Simplify each one of these expressions. Copy them down, and then expand them out according to the exponent rules, and then use your calculator or do mental math to figure out what the new value is. This is called simplifying the powers, simplifying the expression, which happen to be powers, okay? Go ahead and do that real quickly, and then on pause when you are ready, and I will reveal the answers presently. So 5 times 5 is 25, times 5 again is 125. 3 times 3 is 9, times 3 is 27, times 3 is 81. And 81 times 3, if you think about it, that's 240 plus 3 must be 243. When you take a fraction and raise it to a power, it's the numerator is to the fourth power as well as the denominator. And if you expand it out, you see why. So 2 times 2 times 2 times 2 is 16, and 3 times 3 times 3 times 3 is 81. And now you do the same thing with decimal numbers. 8 tenths times 8 tenths times 8 tenths is going to be 8 times 8 times 8, which is 512, but there will be 3 decimal places, so we'll put those 3 back in. If you wanted to see that as a fraction, 8 tenths times 8 tenths times 8 tenths, 8 times 8 times 8 is 512, and 10 times 10 times 10 is 1,000. That's why this is a decimal number that says 512 thousandths. Okay, that concludes our lesson. Thank you so much. This is a very important lesson. We're going to continue doing a little bit of work with this, but then we're going to move on to just working with exponent rules, but we'll continue practicing compound interest, and our chapter test is going to significantly cover this concept that we're learning today. So make sure you get that formula written down and you practice as much as you can using your calculators to get the answers correct. And I'm sure there's a check for understanding for this because it's such an important lesson. All right, take care. Bye.
Hey, feeling good, like I should.